Hello and welcome to your favorite YouTube channel Shridevi Classes, where we inculcate interest and confidence in science and engineering education. Today in our playlist Class 12th Physics, in our subject Electrostatics, we'll discuss the concept of electric potential and potential difference, and we'll find out the relationship of potential and potential difference with amount of work done in moving a unit positive charge from one position of electric field to another position. We'll also find out electric potential and potential difference in the electric field of a point charge. So let's start our study of electric potential and potential difference. A charge placed in electric field experience force, and a positive charge have force in the direction of electric field, and negative polarity charge experience force in opposite direction of electric field intensity. And when such charge placed in electric field are displaced with force, the force and displacement combination involve input or output of mechanical work. When any external agency move a positive charge opposite to direction of electric field in which it will have electric force, it involve input mechanical work. And if charge move itself in the direction of electric force, it release stored energy. In such non-uniform electric field where strength and direction of electric field is different at different positions, the same amount of displacement at different positions depending upon strength of electric field and direction of electric field and displacement involve different amount of work. In a non-uniform electric field, elemental work for elemental displacement of charge is obtained in a differential format. Here this positive charge have force in the direction of electric field, and for external agency positive work is done when it move this charge in opposite direction of electric field. So in electrostatic convention, for bona fide positive work calculation, we consider component of displacement in the direction opposite of electric force, and in electrostatic by convention with this negative sign, elemental work is dot product of force and elemental displacement considered with opposite direction of electric force. So with opposite direction of force, if displacement makes an angle theta and force amount on Q charge in electric field of intensity E is QE, and dot product of force QE and displacement with this negative sign when taken, then it is QE dl cos theta, where theta is not angle between force and displacement but angle between opposite direction of force and displacement. So here dl cos theta is component of displacement in the opposite direction of electric force, and we can also call it dr, and with this negative sign minus dl cos theta or minus dr could be displacement in the direction of force. So this relation is matching to our conventional work done calculation of mechanics, but in electrostatics for positive work calculations we have to move charge in the direction opposite of electric force. So we take a negative sign in our relation and consider angle of displacement with opposite direction of electric force. Here positive Q charge in electric field intensity E have force QE in the direction of electric field. For elemental displacement dl, which makes an angle theta opposite to direction of electric force, elemental work done is given by this relation. Here QE is force, and with negative sign when dot product of force and displacement is done, then displacement is considered in the opposite direction of force. In the dot product, dl cos theta is displacement of charge just opposite to direction of force. So with this negative sign, this dl cos theta is displacement component just opposite to direction of force, and we call it dr. In this non-uniform electric field where electric field strength got different magnitude at different positions, concentration of electric force lines here at position B indicate that electric field is stronger here. So the same displacement dr at position A involve less amount of work, and at position B it involve higher amount of work. So in such varying conditions, to find out total work done to bring a charge from infinity to any position of r distance in electric field is obtained by integration of elemental work, and this would be our total amount of work done in a movement of positive Q charge from infinity to r distance position in electric field E. Electrostatic field is conservative field and it won't have any friction type losses. So when we move a positive charge opposite to direction of electric field or force by a certain displacement in the direction of just opposite to electric force, we have done certain amount of work. Here it is QE into D for movement of this positive charge from B to A, and this amount of work done QED gets stored in this electric system as position of charge, and the same charge in the same electric field, if released and moved from A to B, it can give us QED amount of work in return. So a charge have a capability or potential to do work at different position in electrostatic field, and we say capacity or potential to do work per unit of charge in electric field is called electric potential of that point in electric field. At infinite distance from source charges where electric field is absent, working capacity of charge placed at that infinite position is treated as zero, and total amount of work done in moving a unit positive charge from infinite to any r distance position in electric field is known as potential of that position, and potential is work done per unit charge. Now work is obtained by this yellow highlight relation, and when it is divided by amount of charge will result in potential calculation. Here Q and Q get cancel out, and in this dot product with negative conventional sign, the displacement component is taken as dl cos theta opposite to direction of electric field, and electric field is in radial direction, and elemental displacement along this radial line is dr. So the potential is negation of e dr integration from infinite to r, or in words it is amount of work done in bringing a unit positive charge from infinite to r distance in electric field E. If electric field is produced by a point source charge capital Q, then at r distance from capital Q, electric field is kq upon r square in radial outward directions, and if I make a elemental displacement of positive test charge small q here, then elemental work done is minus QE dot dl, and work done per unit charge is elemental potential difference, and q get cancel out, so it is minus E dl cos theta. Dl cos theta is displacement component opposite to direction of electric field, and along this radial line we call it E dr, and in place of electric field intensity at r distance we can write this relation kq upon r square. And if we see here the amount of work done in this dl displacement or this dr displacement is the same, but same dr displacement at A and B involve different amount of work. So for a positive point source charge capital Q at r distance from it, electric field intensity is kq upon r square radial outward, and elemental displacement dl involve elemental potential difference dv, and it is minus E dr, where E is kq upon r square. Since electric field of point charge capital Q is non-uniform, it is stronger at closer positions, say at position B which is close to capital Q, electric field is stronger than at position A. So same dr displacement involve more amount of work at position B as compared to dr displacement at position A. So the total amount of work done in moving a unit positive charge from infinite to r dash position in electric field can be obtained by integration of elemental potential at different positions, and in place of dv when we write minus E dr and E is kq upon r square, this minus kq as a constant come out of integration. 1 over r square got an integration result minus 1 by r, this minus minus become plus, and for limits from infinite to r dash distance movement, total amount of work done per unit charge is given as, in place of r once we write r dash, second times when with subtraction when we do 1 by infinity that becomes 0, and end result is kq upon r dash. So this is amount of work done in moving a unit positive test charge from infinity to r dash distance from this source charge capital Q in its electric field. Since work is a scalar quantity, so potential is also a scalar quantity, and in the field of positive source charge potential is positive, and in the field of negative source charge potential is negative, and at same distance at different locations irrespective of direction of this r vector, potential magnitude is the same. Potential of a position at a distance r from source charge capital Q is given by V is equal to kq by r. It is inverse of distance from source charge. At double distance potential become half, and at half distance potential become double. Now electric field is a conservative field, and this work done in bringing a unit positive charge from infinity to r distance position in the field of source charge capital Q by external agency gets stored as potential with any charge placed at that position, and if Q charge is placed in a potential of V volt, it has a capacity to perform work equal to Q into V if it is allowed to go to infinity. Hence, work done in moving charge in electric fields gets stored with charge as per its position in electric field, and charge of positive potential or higher potential when released and go to lower potential or infinity, it will release its amount of stored energy. So we can say, in comparison to infinity, capacity or potential to perform work per unit of charge is called electric potential of that point in electric field. Amount of work done in bringing a unit positive charge from infinity to any position in electric field is called potential of that position in electric field, and amount of work done in moving a unit positive charge from one position to another position in that electric field is called as potential difference. So for electric field of source charge capital Q, if we move a unit test positive charge from R1 distance to R2 position, the total amount of work done in this movement is called potential difference between R2 and R1 position in electric field. Now at R distance from source charge capital Q, electric field is kq upon r square, and when we make elemental displacement dl, which makes angle theta opposite to direction of force, then elemental work done per unit charge dv is minus e dot dl, and dot product results in dl cos theta, which is along radial line dr displacement. Since dr displacement is considered opposite to direction of force, so we also use a negative sign in this relation. So this would be elemental work done for small displacement dr. Now in non-uniform electric field, elemental work done at position B where electric field is stronger will be more. So to find out total amount of work done from R1 position to R2 position, we use integration technique, and total amount of work done in moving a unit positive charge in the field of source charge capital Q from R1 distance position to R2 distance position is obtained by this integration. Here minus kq is a constant, 1 by r square integration is minus 1 by r, and when we take limits, before limits this minus will get cancelled out, and in place of r, once we have to write down r2, which is final limit of this integration, the final position of test charge, and this is initial distance position of unit positive charge in the field of source charge, and this kq 1 over r2 minus 1 over r1 is potential difference between r1 and r2, and since kq upon r2 is amount of work done in moving a unit positive charge from infinity to r2 distance, it is potential of second point, and similarly kq upon r1 is potential of first point. So we can say potential difference is difference of potential of two positions. Now since this potential difference is obtained by integration techniques, and integration techniques doesn't depend upon path, amount of work done in path 1 or path 2 or path 3 or elsewhere with same initial and final distance position from source charge results in same amount of work done in moving a unit test positive charge from R1 to R2 distance position. So potential difference doesn't depend upon path followed for the movement. If we bring a unit positive charge closer to a positive source charge, R2 distance is smaller than R1 distance, so 1 over R2 is greater than 1 over R1, and this amount of work done per unit charge is a positive amount, so the potential will increase. Similarly, if we move from high potential closer to positive charge position to a lower potential position, far away position from source charge, the potential will decrease. And with any potential difference, if Q positive charge is moved, the amount of work done is given by Q delta V, and this work could be positive or negative depending upon sign of charge and sign of potential difference. If a positive charge is moved from low potential to high potential with positive potential difference, amount of work done by external agency is positive. Similarly, a negative charge moving from high potential to low potential, both charge and potential difference is negative, but the work done is positive. Assume that this informative learning video has made your understanding about concept of electric potential in electric field thorough and crystal clear. Our other video in the same playlist which relate potential gradient and electric field intensity and work done calculation and potential difference will make your understanding better and stronger to face any examination. If you found this learning material useful, do share it with your friends and do join our membership to get study support material and online classes support from Shridevi classes. Thank you very much.